Hi guys. So today we'll be discussing week 10 summary and I'll just share my screen and then we'll start with it. Is my screen visible? And I hope I'm audible to clearly audible to you people.
Yes, ma'am.
Okay. So week 10 is just one second. Week 10 and 11 both are about graph theory. We'll be learning some basics of graph theory here. And graphs, so before starting with graph theory, let's just see what graphs are. So graphs are just ones. So that two graph consists of two things. One are your vertices and the other is edges. So these vertices are represented by these dots in your graph, and then the edges are what joins two vertices. So this is called an edge. So these are called edges. And then obviously these dots, which you have to mention like V1. So this is first vertex, second vertex, third vertex, fourth one, fifth one. So these are vertices, and then these are the edges. And this collectively is called a graph. Where this is the set of vertices, this is the set of edges, capital V and capital E. So let's first discuss a problem. There's some specific sort of problems on graph theory. The first one is graph coloring problem. Why do we discuss the graphs and all stuff? It's to know that your vertices could be anything. Like we can have an example where your vertices could be classes, and then let's say vertex 1 could be English class, vertex 2 could be maths class, and the third one could be science class. And then if there is and these edges could represent if there are common students who are studying both or who are taking both these classes. So if there's a student, even if there's one student which is common in these two classes, then we can say that our edge between E and M represents that there is a student who attends, at least one student who attends both English classes and math classes. Same can go with these. And if there's no edge between E and S, that means there is no student who attends both English class and science class. So that's what your graphs are for. They're for different situations, your vertices and edges could mean different things. So let's do the first problem. First one is graph coloring problem. So graph coloring problem is basically, let's have an example first. Let's have this. So what do we do in a graph coloring problem? And then we'll come to an example too. Our aim is to color these vertices with minimum number of colors such that no two adjacent vertices. Okay, so two vertices are called adjacent vertices if they have an edge between them. So this vertex, this one, and this one are adjacent because they have an edge. These two are not adjacent because they don't have an edge. So because these two have an edge between them, so our aim is, what's our aim? Our aim is to color edges in such a way that no two edges which share an edge have the same color. So that means if you're coloring this red, let's say I'm coloring this one red, then every edge, every vertex that has an edge with this vertex cannot have red color. So this is, first is this cannot have red color, this cannot have red color. then it's this. This cannot have red color. Now these two, this one and this one, they don't have a direct edge with this B vertex. That's why we can color them red. Our aim is to use minimum number of colors to color this entire color all the vertices in such a manner that no two adjacent vertices have the same color. That's our aim, right? That means if two vertices are sharing an edge, they should not have same color. These two cannot have same color because they share an edge. These two can have same color because they don't share an edge. So this could be red. And then so for the other ones that share direct edges with these, with this or this, any of these, we should use a different color for that. Let's say you should use green for this. Then these two do not have an edge common, so you can use green for this one too. And this does not have an edge common with this one or this one, right? With both of these, this does not have an edge common, so you can color this green. Now let's say if instead you had this, if you had an edge here, if this was an edge and this was an edge too, then I'll color this green. But now I can't color this or this green because they have a direct edge with this green. So I'll have to choose a separate color for this one. So let me just choose blue for this one. And then because this and this does not have an edge common, so you can color this blue. That's your graph coloring problem. Now, where do we see these problems in real life? First would be, we could take one example of, let's say you have subjects here. Let's say this is, what we could have had is, let's say this was a math subject, or let's say this was math one subject, then this was math, or let's take this is math, this is Hindi, then this is English, this is science, let's say, this is history, let's say, and let's say this is geography. So the vertices represent your subjects. And then let's say these edges. So what we're trying to do is we're trying to make a date sheet. And so if these two, or let's not even take this thing. Let's take something different. Let's take physics here. And let's take chemistry here instead. So that would mean, so if these were the subjects, and let's say these edges represent, this is just an example. So let's say these edges represent a student who has taken both these subjects. Let's say if there's an edge between two subjects, if there is a student who has opted for both this subject and this subject, then you can't have the exam of this subject and this subject at the same time, right? Let's say there's a student who has opted for both maths and chemistry as subjects, then you cannot have the exam of these two on the same date at the same time, right? So if you were to make a date sheet, you would avoid putting these two subjects, because an edge here means, edge in this particular example means a student has opted for both subjects. Yeah, at least one student has opted for both subjects. So if you have edge V1, V2, that would mean a student has opted for both subjects V1 and V2. And then you cannot have the exams of V1 and V2 on the same date, right? So that's the idea. So if you were to make a date sheet, or just 1 second. So let's remove these first. That's not needed. Okay. So you have maths. Let's say you have a date fixed for maths. Then chemistry, and chemistry as a directed. That means there's a student who has opted for chemistry and maths both. There's an edge between maths and geography too. That means there's one student who's opted for both these subjects too. That means you cannot have the exam of maths and chemistry on the same day and maths and geography on the same day. That means if maths, let's say you're having maths today, then you cannot have the exam of geography and chemistry on the same date, right? That means, let's say this green one, green is 30th April. So if maths exam is on 30th April, you can't have chemistry and geography exam on 30th April. So maths can be here. Then next one, geography and chemistry you'll have to have on different dates. And there is no student, because there is no edge between chemistry and geography. That means there's no student that has this subject who has opted for both these subjects. That means you can have the exam of chemistry and geography on the same date. So let's say that date, let's call that date to be 31st April. Sorry, there's no 31st April. Let's have 1st May. So 1st May, that means you can have the exam of chemistry, geography, and physics on 1st May because there are no students who opted for chemistry, geography, and physics, right? So you can have exams here. Chemistry, physics, and geography could be here. And maths, English, and this history can be here. Is this okay? Can we move to the next topic if this one,
So basically, these are the disjoint.
these are disjoint, but yeah, you can call them disjoint. Disjoint sets, but this is not about the sets. It's about coloring them in such a way that no two has the same, no two share a common edge. That's it. You can see it that way too. That's also fine. Can we move to the next topic? If anyone has any doubt, you can unmute yourself and ask. And let's move to vertex cover then. The vertex cover is basically, vertex cover is, let's call this is a set, and let's call that set to be B dash. So it's a set of vertices. So this is collection of all the vertices of the graph. And this is a subset of set of vertices. That means it can have some vertices. And what vertices can it have? It can have a, let's do it with an example first. So let's say you have this graph. Let's say you have this. Then vertex cover basically means you have to collect the vertices in such a way. So this is a collection of vertices, right? Your vertex cover is, let's call it VC only. Vertex cover is a collection of vertices, and how do you collect those vertices? You collect them in such a way that each edge, so V1, V2 is an edge, right? How many edges are there? If we edges are written in this manner. So this edge is written as V1, V2. Then this is written as V2, V4. So what is the collection of your edges here? In this graph, you have these edges. The set of edges is V1, V2, V2, V4, then V2, V5, and then V4, V5, V3, right? Yeah. These four are the edges in your graph. If this is your graph, this is the collection of edges, right? And you have to collect vertices in such a manner that from each edge, there should be one vertex. Now you can have more than one vertex, but our aim is to find a collection of vertices such that from each edge, you have one vertex in this set, in the set vertex cover, right? So vertex cover is you have one edge V1, V2. So we need one vertex from here. Let's take V1. You can also take V2. That's also fine. Let's take V1. This edge is covered. Then come to this one. You can take V5. Then come to this one. You can take V4. And then we're done. So now from each edge, you have one vertex, right? From this edge, you have this vertex. From this edge, you have this vertex. From this one, you have this vertex. And from this one too, you have this vertex. So this is a vertex cover.
We can also have this vertex cover as V1, V2, and V3.
Yeah, you can do that too. There is no unique vertex cover. You can have more than one vertex covers. So you're saying V1, V2, and V4, I guess.
V3.
Right? That's also fine. You can have V3 here. No,
V1, V2,
you
V3.
can't have V3 here. You can have V1, V2, V3. You can also have V1, V2, V4. That's also fine. So if you have V1, V2, V3, then this is covered because V2 is here. This is covered, V3. This is also covered. Or you can have V1, V2, and you don't need V1, right? Wait, if you have V2, just 1 second.
We can have V2 and V3 because V2 is present in
Just
all
1 second.
three.
There's some connectivity issue from my end. Just 1 second. Yeah. So I was saying if you have, because a graph looks like this, you don't actually need V1 because you already have V2 here. So you can just remove V2, V1 from here. If V1 is also fine. If you keep V1 here, that's also a vertex cover. If you keep V1, V2, V4 here, that's also a vertex cover. But there's something called minimum vertex cover. Minimum vertex is to find the collection of minimum vertices such that every edge is covered, right? So minimum vertex cover then will be V2 and V3. So if you have V2, V3, V2 covers this edge, and this edge, and V3 covers the one left, this one, right? Similarly, uh, you can also have another one, which is V2 and V4. That's also fine. So V2 and V4, the same thing. V2 covers this one, and this one, and V4 covers this one. That also works. So these two are minimum vertex covers. They're also vertex covers. This one is a vertex cover, but it's also obviously not minimum, right? This is not a minimum vertex cover. This is also not a minimum vertex cover. Is this one clear? The minimum vertex cover thing. An example could be, let's say you have corridors here. Let's say these are corridors. These are some rooms, or these are some corners in a building. And then these are the corridors connecting these corners. So the edges are, if you have this, let's say these two are rooms, V1, V2, V5, all the vertices are rooms, and then let's say these two are corridors connecting the rooms. Or this is, let's say, just a corner. V1, V2, V5, all of these vertices are just corners, and these edges are representing a corridor. So if, because there's no edge between V1 and V5, that means V1 and V5 does not have a connecting corridor, and V1, V2 has a connecting corridor. So if you have, and let's say you have to install CCTV cameras, so you can install one here that would take care of, or you can just install one here, right? You can install one here that would take care of this corridor, and this corridor. And you can install the other one here that would take care of this corridor, the one left. So only two are enough, right? This is one example of vertex cover. Uh, does anyone have a doubt so far? We can discuss that. Otherwise, we can move to the next topic, which is independent sets, or an independent set. So what is an independent set? Let's say you have this graph. Then, then an independent set is basically the collection of vertices again. And you have to collect vertices in such a way that no two vertices share an edge. That means if you have V1 here, if you have to have an independent set and you start with V1, then you can't have V2, because V1 in this set you cannot have. If you want this set to be an independent set of vertices, then you shouldn't have V2 here. You can have V5 here because V5 and V1 do not have a common edge between them, right? And then the next vertex should be such that it does not have an edge with V5 and V1. So V4 has an edge with V1. We can't have that. V3 does not have an edge with V1 and V5. So you can have this here. So this is an independent set. If you start with V2, then you can only have V3, because V2 only, there's only one vertex with which V2 does not share an edge. With all the others, it does share an edge, right? So only V3 is possible here. This is also an independent set. And you can take the same example here, the one that we have for graph coloring problem. You can have the same one here. Let's say you have to figure out which exams can we keep, which subject exams can we keep on the 30th April. Then you'll have to figure out an independent set, right? An independent set from here. This is an independent set. This set is an independent set. This is another independent set. So these are called independent sets. This is called an independent set. This is also called an independent set. The same example works here. That's about independent sets. Then next we have
Repeat the independent set. I lost my connection.
independent sets is basically collection of vertices such that no two vertices have common edge. So if I have V1 here, I'll have to make sure that other vertices that I'll include in this set do not have a common edge with V1. So if I have V1 here, I can add V5 because V1 and V5 do not have a common edge. Then I can add V3 because V3 does not have a common edge with both V5 and V1. So it has to be like V1 and V5 should not have an edge, V5 and V3 should not have an edge. That means this vertex should not have an edge with all the other vertices included in your independent set. That's it. That's your independent set. And in the graph coloring problems, you could just say that these three constitute, these three form an independent set, and these three form another independent set. That's it. Is that okay? Can we move to the next topic? Okay. So our next topic is of matching and perfect matching. Matching is basically collection of edges where you collect the edges in such a way that your edges are you have to collect edges that are disjoint. So that would mean that this is the set of all the edges in your graph, right? E, capital E represents the set of all the edges. So let's say you have this thing. This is V1, V2, V3, and V4. Then this set is equals to V1, V2, V2, V3, and V2, V4, right? So out of this collection, you have to have a collection M, which is called your matching, and you have to collect edges here such that the edges are disjoint in the sense that they should not have a common vertex. So if this is this is an edge and this is an edge, then we have a common vertex here, right? V2, V2. Similarly, here we have a common vertex V2, V2. Here also we have a common vertex V2, V2. That means if you have V1, V2, if you want to keep V1, V2 in your matching, then you cannot have any other edge here. That's it. That's one matching. Then some other matching could be, matchings are not unique either. Like it's not like you can only have one matching. You can have more than one matching for a given graph. So if you want to have V2, V3, then you can have okay, this is a very, V2 is everywhere, right? That's why you cannot have anything else. And let's say you have V1, V4, V5 too. So if this was it, you will have V4, V5 here. And then you can have, in this matching, you can have V4 and V5. And here too, you can have V4 and V5. So this is basically, and then let's first discuss perfect matching. The perfect matching is a matching, obviously. That means it's a collection of edges such that no two edges have a common vertex. It's a matching, first condition. And then the second condition is that every vertex should be covered. Every vertex covered means that if you're having this, like if you have this matching, then in this matching, you can leave vertices, right? You have V2, V3, V4, V5 here. You have left V1. V1 is not here. Similarly, here you don't have V3. So by covering all vertices, or you can say all vertices should be present or should appear once in the set, in this set, right? So that's your perfect matching. This is not a perfect matching. This is not a perfect matching. How can we have a perfect matching for this one? Can we have a perfect matching for this one? Your graph had, forget about what the graph was. Your graph had 5 vertices. So if you have five vertices in a graph, then can you have a perfect matching there? Because for a perfect matching, you need a matching. That means you need collection of edges, and each edge will have 2 vertices, right? And once you've had 2 vertices here, you cannot have those 2 vertices another time. You cannot have them repeated. That means there'll be another set of 2 vertices, then these two, and then another two, and then another two. So it's always even, and you have to cover all vertices, right? So if you're covering all vertices and each time you add 2, That means you can only have even number of vertices in your graph. If you have odd number of vertices, let's say you have 5 vertices, V1, V2, V3, V4, and V5. No matter what the graph is, you cannot have a perfect matching. Because let's say if you will take this thing, then you will have, let's say you're taking V1, V2. Then you can't take V1, V5. So for V5, and you have to have every vertex in this set, right? At least once. So V5 has to be here. So you need an edge with V5, and then there's only one edge with V5. That means you can only have V3 here. That's the only option left for you. And then V3, so V1, V5, V3 are covered so far. V1, V2, V3, and V5. These are covered, and V4 is left. And there is nothing left for V4 to pair with, right? So V4 will always, some has to be left. If you will take this, V4 is left. If you will take something else, some other matching, then some other vertex will be left. Let's say you start from here, then you will have V2, V4 here. Then because V2 has been covered and you cannot have it the second time, that's the rule for matching. So you cannot have the edge V2, V3 here. That means you will have to take V3, V5. That's the only choice left for V3. V3 has to appear here. It cannot appear with V2, so it will have to appear with V5. And then V5, so these are covered. V1 only had two choices, V1, V2, and V1, V5. V2 is already there. V5 is also already there. That means you cannot have V1, V2 or V1, V5 here, right? That means V1 is left this time. So you cannot have a perfect matching here. But if you add another one here, let's say V6, and then this was it, then you could have V4 and V6. And you always start, while finding the perfect matching, always try to, you have to start with the one which is mapped with just one vertex. So if it's only connected to, or if it only has an edge with one vertex, like this one, then you should start with this one. Because V4 has two choices, but V6 only has one choice, V4. So this edge has to be in the set of perfect matching. This is a perfect matching. And what's not a perfect matching? If you have V1, V2, V5, V3, this is still a matching, but because all vertices are not covered, that's why it's not a perfect matching. This is just a matching and not a perfect matching.
Ma'am, can we
Yes.
consider it like a odd or even number? If we have either even number as is, then we can say that it is perfect match, and if it is odd, then it is not perfect match.
No, you can't. Because if you have, let's say this was your graph. If you have odd number of vertices, then you can say that you cannot have a perfect matching. But if you have even number of vertices, then you can't conclude. You will have to look at the graph. Like this, if you have this graph, then you cannot have a perfect matching here. Because V6 cannot be paired with anything. Right? So this graph cannot have a perfect matching, even though it has even number of vertices. But this graph can have even number, can have a perfect matching. And it, so the rule is has a perfect matching. This implies even number of vertices. That's it. If you have even number of vertices, that doesn't mean you will have a perfect matching. Is that okay?
Ma'am, could you please explain the last line once again?
This one.
Yes, I missed it a bit.
We just discussed here that when we had 5 vertices, we could not find a perfect matching, right? No matter what your graph is, if you have, let's say you have 3 vertices here, no matter what your graph is, this or this or this or this or this, no matter what your graph is, you cannot have a perfect matching because it has odd number of vertices. So the rule is if you have odd number of vertices, there does perfect matching does not exist. We have discussed why, right? But if you have even number of vertices, you cannot guarantee if a perfect matching will exist or not. Then you will have to look at the graph. It depends on the graph then. So your rule becomes if your graph has a perfect matching, that means you'll have even number of vertices. But the converse of this is not true. Even number of vertices does not imply graph has a perfect matching. Is that okay?
Yes, ma'am.
Okay. Then we have the topic of adjacency matrices. So what, oh, before that, we'll discuss this. Let's discuss directed graphs and undirected graphs first. So directed graphs are the ones with directions. That means we've just studied these type of graphs, right? V1, V2, V3, and V4. But if we include directions here, that means let's say this is one place and this is some other place, and there's only one. You can only go from here to here. Let's say there's a system which lets you go from V1 to V2, but there's no system, or let's say there are flights here. This one is an airport, this one is another airport. These vertices are airports, and then let's say there's a flight from V1 to V2. So you can go from V1 to V2, but there's no flight from V2 to V1. So that means you cannot come from here to here, right? Then you'll have to mention the directions too, that this is directed towards this. Let's say this is directed towards this, and this is directed here. So these are called directed graphs, and undirected are where you do not have directions. Like let's say you have let's say you have a graph of friends. So let's say these are just people V1, V2, V3, and V4. And then there is an edge between two if they are friends. And there's no edge if they're not friends. That means if V1 is a friend of V2, V2 is also a friend of V1, right? So then you don't need directions there. It automatically assumes that it's directed in both directions. That's your undirected graph where you don't need directions. Like let's say you have this is a place, this is some other place, and there is a road from V1 to V2. So if there's a road from V1 to V2, that means V2, if V1 and V2 is V1 is connected to V2 by a road, V2 is also connected to V1 by a road, right? So in that case, we use undirected graphs. Now let's come to adjacency matrices. So if you first write the vertices here, V1, V2, V3, all the vertices here, and then all the vertices here too, V1, V2, V3, V4. So this is basically, if you have an edge from here to here, then you write a 1 here, else you write a 0. So adjacency matrices are matrices, obviously these are matrices, but they can only have entries as 1 and 0. 1 if there is an edge between V1 and V2. So if there's an edge between V1 to V2, then we write a 1 here. If there's no edge, then we write a 0, right? Like this one. And these diagonals are all 0 because V1 to V1, we just write 0 here. So V1, V1, this entry is 0, V2, V2 is 0, V3, V3 is 0, and this is 0. Then coming to the other entries, this one, from V1 to V2, if we take this graph, we have an edge from V1 to V2. That means you'll have 1 here. Then we have an edge from V1 to V3. No edge from V1 to V3, so a 0 here. No edge from V1 to V4, a 0 here. Then coming to this one, we have an edge here from V2 to V1. So 1 here. From V2 to V3, 1 here. No edge from V2 to V4, 0. For V3, 1 here, 1 here, and 0 here. And for V4, 1 here and 0 everywhere else. So this is your adjacency matrix for this graph, which is an undirected graph. So in an undirected graph, what happens is, if you have studied about symmetric and skew symmetric matrices, then you will see that this is a symmetric matrix, which means Aij symmetric matrices are basically these. Aij should be equal to Aji. That's Aij are entries of matrices, right? Like this one is 1 1 entry A11, A12, A13, A21, A22, A23, A31, A32, and A33. So we're calling this as IJ thing. That means if your A12, Aij equals to Aji means A12 should be equals to A22, A21, A13 should be equal to A31, and A23 should be equal to A32, which is true for this one. For this matrix, it's true, right? And then that's the case for undirected graphs, because whatever is the entry from V1 to V2, there are no directions. Yes.
To read that what you said, A12 means A is uh, A2 has one edges, right? Just now you just erase it. Erase 2 1.
Yeah.
Means 2 to 1 has one edges. How to read this?
Okay. This is how we represent. Let's say you have a random matrix A, then the entries are written like this: A11. That means this first entry is written as A11, then this is written as A12. This is 1/3 entry. This is A2 first entry, A2 second entry, A2 third entry, A2 fourth entry. So from here, your A11 entry is 0, right? A12 entry is 1. A13 entry is 0 again. And then you have A142 in this one, which is again 0. That's how you continue here. So what I meant here is, if you A12 is, if your A12 is 1, that means for this graph, if your A12 is 1, that means there is an edge from V1 to V2, right? That's what we
Yes.
discussed here. If there is a 1 here, that means there is an edge from V1 to V2, right? But because this was an undirected graph, that's
This one
why,
is unsolved means matrix. This one A11 and A12, A13, right? And this one is solved.
solved as in,
Means
this is,
A11.
this is just notation. This is notational, nothing else. You don't have to
Okay.
bother about this thing. These are just notations. Instead of writing numbers, I'm using notations. That's it.
Okay.
So this was what I meant here is the entire point of this discussion was, if you have an undirected graph like this one, if you have an undirected graph, then this entry V1 from V1 to V2, this one, and from V2 to V1 is going to be same, because if there's an edge from V1 to V2 and the graph is undirected, that means it does not have directions. It's not like this. That means it's considered both ways, from V1 to V2 and V2 to V1, right? So in an undirected graph, it looks like this. If V1, V2 is 1, V2, V1 is also 1. But let's say if this graph was directed, V1, V2, V3, and V4. Our graph was this. And let's say now we have directions. This one, and this one. This edges in both directions, this one and this. So how would this look like? So first entry will be, I'm not writing V1, V3 here. First entry will be from V1. The diagonal entries are 0, right? And then from V1 to V2, you have an edge. That means you'll have 1 here. Then from V1 to V3, you don't have an edge. You'll have 0 here. From V1 to V4, V1 is here, V4 is here, right? From V1 to V4, you don't have an edge, so you'll have a 0 here again. Then you'll come to the second one, V2. From V2 to V1, you do have an edge directed from V2 towards V1, right? So you'll have a 1 here. Then from V2 to V3, there is no edge, right? You have an edge from V3 to V2, but not from V2 to V3. That's why this will be 0. Then from V2 to V4, again 0. And in this manner, it continues. So the difference here is, here you had a 1 here, but now you have a 0 here. And here, if you have A12 entry, A12 means this first row and second column. So this entry. These are columns, these are rows. So A12 is basically this entry. A12 should be equal to A21. A21 is this entry, which is not true for this graph. It's true for A12 and A21, but it's not true for this one. V23 and V32 it wouldn't be true for. So A23 and A32 is not equal for this one. A23 is, what's A23? A23 is 0 because you don't have an edge from 2 to 3. So this is 0. But A32 is 1 because you have an edge from 3 to 2. So this is 1 and these two are not equal. And they're always equal here in undirected graph. Then we have the topic of in degree and out degree. So let's first discuss what's degree of a vertex. Degree of a vertex is, let's say we're taking V1, and this is the example that we have. Let's take V2. So degrees are discussed for undirected graph. If you just see degree, that means they're talking about undirected graph. If you see in degree or out degree, in degree of V2 or out degree of V2, that means this is for, so these two are for directed and this is for undirected graphs. This term is used for undirected graphs. Like let's say you have this thing. Let's say you have this graph, V1, V2, V3, V4, and V5. Then as long, if it's, now this is undirected, right? So the degree of V2 is the number of edges that it's connected, that it has, that it lies on, right? So it lies on this edge, and this edge, and this edge. That means it lies on 4, right? So the degree of V2 is 4. Similarly, degree of V4, what's the degree of V4? The number of edges it lies on. So it lies on this edge, and this edge. That's it. So the degree of V4 is 3. Let's do degree of V1. The degree of V1 is 2 edges, 1 and 2. So it should be 2. Degree of V3 is again 2, 1 and 2. And what's left? Degree of V5 is just 1 because it only has one edge here. That's it. So these are called degrees. And let's say now we take the same graph here. Where you have V1, V2, V3, V4, and V5. And you had this connected to all the others. So we've taken the same graph again, but this time we're also taking the directions. Let's say the direction of this is this, direction of this is this one is this, and this. Then we talk about in degrees and out degrees of a vertex. So in degree means the number of edges that point towards the vertex, right? So let's say if you have V1, then there is no edge that point towards V1, right? There's no incoming edge. That means the in degree of V1 is 0. In degree of V2 is 1. There's one incoming edge. Okay, there's this one too. Right. This is 2. And similarly, you can do for all the other vertices. And with out degree means the number of edges going out of that vertex. So let's say you have V2, then the out degree will be this. There's
2.
only one edge. Okay, that's also 2. We have that. That's also 2. For V1, it will be again 2. And similarly, you can do for all the other vertices. That's out degree and in degree. And then we have a concept of reachability. So reachability is basically
Ma'am, could you please explain the degree thing again? I'm okay with in degree and out degree, but not the degree thing.
this one. This is basically the
Yes.
number of edges that this vertex lies on. So let's say you have V2, because there is no concept of incoming edge and outgoing edge, right? So there's just one edge. So the number of edges that this is connected to, or that this vertex lies on, is the degree of this vertex. And it only, if you see degree, that's only for undirected graphs. For directed graphs, you see the term in degree and out degree. So degree of V2 is because it has 4 edges from connected to it. That means it should have 4 degree, right? 1, 2, 3, 4. So for V4, you'll have 1, 2, 3. You just have to count the number of edges that it's connected to. That's it. Or that it lies on. Like this one lies on 3 edges, 1, 2, 3. That's why it has 3 degree. Is that okay?
Yes, ma'am.
Okay. So next topic is a reachability. Reachability means, let's say you have this, there's some graph, right? These are the vertices here. Then let's take a very simple example. Let's say I'm here. These are places. And this means if we have a road here or not between V1 and V2. So can I go from V1 to V4 following these roads, obviously?
No.
We're assuming that there's no other path. So you can't go from V1 to V4, right? You can't go from, so what points can you go from V1? You can go to V2 and that's it, right? You can't go to any other point from there. So only V2 is, that means only V2 is reachable from V1. That's it. That's reachability. If you look at V2, which all vertices are reachable from V2? No vertex is reachable from V2, right? If you are at V2, if you are at this place, you can't go to any other place. If you are at V3, then the reachability is, what are the reachable vertices? V2 is reachable, V4 is reachable. If you had this here, then V5 is also reachable from V3, right? You can go from V3 to V4, V4 to V5. That's why V4, V5, V2. These all are reachable from V3. Is that okay? That's called reachability. And
No, ma'am, please explain it again.
okay, let's say you have this thing. Let's take this graph. Reachability basically means if you have one, let's say these are some places. That's not the, this is a particular example that we are describing the graphs as. That won't be given every time. This simply means, can you go from, if you're considering, and this is called a path, by the way. If you have, we say that V1, there's a
And
path
is
from
there
V1.
gap V2 to V3? This is gap or this is this here you made a graph V1 to V2 and 3. I cannot see. Is it joining or it is there is gap?
Which one?
Yes, this V2
This one?
V1 to V2. Yeah, in between, in middle, is there gap?
How does that gap matter? It's if you see an edge from V1 to V2, this is an edge from V1 to V2. This is an edge from V3 to V2. What's your doubt?
Okay. So V1 to V2 I can reach, but V1 to V3 also I can reach, right?
You can't. That's what I'm saying. If this is consider this as V1, and then you can go from here to here because it's directed in this direction. So you can go from V1 to V2, but you can't go from V2 to V1. So how will you go to V3 from V1? You can't go from V1 to V3 directly because there's no edge. So you'll have to go here. And from V2, you can't go to V3. So you'll have to come here. From V4 also, you can't come to V3. Then you'll have to go here. From V5 also, you can't come to V3. That means there's no path from V1 to V3, right? These are called
Yes,
paths.
ma'am.
V1 to V2 to
So,
V4 to
so
V5. This is
because
called a
of the
path.
direction, we can decide that we can go or we cannot go.
Yeah, that's why there are directions.
Okay, ma'am.
This is a directed graph. And when you're given a directed graph, if you're not given a directed graph, if there were no directions, then yes, you can go from V1 to V3. But if the directions are given, that means you cannot go from V1 to V3. So the reachable vertices from V1 are, you can reach V2, you can reach V4, you can reach V5, but you can't reach V3. Similarly, from V3, you can reach V2, you can reach V4, you can reach V5,
Oh,
but you
okay,
can't reach
ma'am.
V1.
Okay, ma'am. Got it.
Okay. And then we have the maximum number of edges of, let's say your graph has n vertices. Number of vertices is n, let's say. Then what is the maximum number of edges it can have? Let's say if I have 3, then or 4, I'm joining all of these. I'm joining this one to all the others. Maximum number of edges, what does maximum number of edges means? That means every possible edge, I'm drawing it here. So if it's possible, I'm drawing it. So how many maximum number of edges are possible here?
4.
If you have, yeah, here you will have 4. You will have 1 from here. Then the 4 is not the answer here. We're talking about edges, not vertices. Maximum number of edges.
Ma'am, it is n minus 1.
Yeah, so let's do it for 4 vertices first. This means you have to have an edge from every vertex to every other vertex, right? Let's say this, we're taking the example of a directed graph. If it's a directed graph, or if it's a directed graph, that means this edge, and this edge. 3 edges so far. Now we'll come to this vertex. So we'll have this edge. And these two are counted differently. So if you have this edge and this edge in a directed graph, then these are counted as 2 edges. They're not counted 1. So it's generally given like this, V1 to V2, that they are counted as 2 in directed graphs. In an undirected graph, it's counted as just 1. So there are 2 here, from here, and then you'll have 1 here and 1 here. So 3 from here. So what we're doing is, for each one, we are connecting it to the other 3, the left ones, right? So this one, we connected it to the 3. For this one, we connected it to the other 3. For this one, we connected it to the other 3. For this one, we connected to the other 3. That means you're taking 3 to 4 times. That means 4 times 3. So a simple formula would be n vertices n minus 1, right? Because you will be adding n minus 1 n times. That's what we're doing, right? If you generalize this thing, it's n minus 1, n minus 1, n minus 1 added n number of times. So you will have number of edges, maximum number of edges possible, n minus 1. But if you have an undirected graph, this is for directed one. Maximum number of edges for undirected will be, so if you look at this particular example, you can have this because it's undirected this time, right? So if this is done, and this is done, then basically this one is already done, right? So you can't have another edge here. You will not draw it again. So you only have these. And then you'll only, for this one, you'll only draw this. That's it. So the formula here becomes n minus 1 by 2. Why? Because these are counted 2 times. This is counted 2 times. And in an undirected graph, we only count it as 1. That's why we're dividing by 2 here. So if this was the case, if you only have 2 vertices, for example, then in an undirected graph, you'll have 2 edges, right? Sorry, in a directed graph. But in an undirected graph, you'll only have 1. You're dividing by 2. That's it. You don't have to get into how we get this. You just have to know that we have maximum number of edges n minus 1 by 2 for an undirected graph. And for a directed one, it's this. Then we were talking about reachability. So there are algorithms to discuss or to see if one point is reachable or which all points are reachable from a given point. And the two algorithms are, one is BFS. It's called breadth first search. And the other one is DFS. We'll discuss that later. What is BFS used for? This is to discuss the reachability of points from a given point. So let's do it with an example. Let's say you have this as a graph. And your graph could be even more complicated. So it's not a very good idea to just check one by one, right? So what we do is we perform breadth first search. There's another algorithm too, which is depth first search. So we'll come to that one later. Let's first discuss this one. Before starting with this, there's something called a queue, a convention that's used here, which is you keep track of what has been discovered so far. Discovered as in what has been reached so far from a given vertex. So let's say you have to find the vertices that are reachable from V1. So you're starting from V1. So you write V1 here first in your queue. And breadth first simply means that you explore the entire breadth of a given vertex. There'll be two terms that I'll be using. One is visiting a vertex and the other one is exploring a vertex or done exploring a vertex. So visiting a vertex means when you visit this vertex, like from this one. And exploring means, or done exploring means, when you are done visiting every vertex from this vertex. That's directly connected to this one. That means this one is directly connected to this one is directly connected to this one. If you've discovered all of these via V1, then we say V1 is explored. We'll see that here. Let's say we started from V1 because we want to see which vertices are directly connected from, which vertices can you reach from V1 if you
V2,
follow these direct. Sorry, what?
V2 and V4.
V2, V4. Okay, let's see. Let's do it using this approach. We have an approach for it, right? And we have to see how this approach works. So we first write V1 here. And we first explore the breadth of this. Breadth in the sense that you visit the vertices that directly have an edge with it. V2 has a direct edge with V1. V4 has a direct edge with V1, right? So V2, you write V2 here and then V4 here. That means this vertex is done and we're done exploring this vertex because we have discovered all the vertices that have a direct edge with this one. That means we're done exploring this vertex and this is done. Then we come to V2 You could also begin with V4, that's also fine. We come to V2 and we see which ones are directly connected to which vertex is this. V6. So V6 is directly connected to it. You can go from V2 to V6 and that's it, right? So only V6 is there. So V2's breadth or V2 has been explored, right? Because there's only one vertex that's directly connected to it and we've mentioned it here. That means we're done exploring V2. So V2 is also done. Then we come to V4. We have to go in this order. First, this one gets done, then this one gets done, then we come to V4. So V4 has a direct edge with V5, and that's it, right? So you'll have V5 here, and you're done with V4 because there is no other vertex which is directly connected to V4. And let's say, let's have this one. If we had this edge too, then we wouldn't mention V2 again in the queue because V2 has been explored, right? V2 is done. We're doing this entire thing for reachability and V2's reachability has been discovered. So we don't have to write it again. So while writing the vertices directly connected to V4, you only write the vertices that has not been visited so far. So you only write V5 here, not V2 again. We don't write V2 here again. And then we were on V4, right? So V4 is done. Then coming to V6, next in queue is V6. So we have to explore V6. V6
V5
is
already completed.
yeah, that's also done. That means V6 is also explored. We say this vertex is explored when every vertex that's directly connected to it, that directly has an edge with it, has been visited. Then we say that it's explored. So V6 is explored. Then what's left?
V5 explored.
And yeah, so we'll come to V5 next. This one is done. Next in the queue is V5. And V5 does not have an outgoing edge. That means V5 is also explored. And this is the end of it. That means these are the reachable
What we
vertices.
did with V3?
V3 doesn't come here. So that's what we'll see what that means. We started from V1 and we visited all the vertices that were possible. So in this manner, if you go, this means you've written all the vertices that you can reach from V1. And if V3 is not in the queue, that means you can't reach V3 from V1. So V3 is not reachable from V1. That's what it means. That's why V3 is not in this queue. So the reachable vertices from V1 are V2, V4, V6, and V5. These are the reachable vertices. You can start with other vertices too. So if you have to find which vertices are reachable from V2, you start from V2. If you have to find from V3, start from V3. Start your search from V3. Should I do with some other vertex too, or is this clear? Or let's do one more example on this. Let's say you have this. Do we need to discuss one more example or is this one enough?
Ma'am, it's clear for me. I don't know about the others.
Yes, ma'am, it's clear.
Okay. So then
It's clear.
let's move to what's a BFS tree. So a BFS tree, a tree is basically a minimally connected set. So we'll discuss tree first. What's a tree? It's a minimally connected set. And for that, you need to know what is a connected set. So let's start with the definition of a connected set. A connected set is basically, let's say you have this. So this is connected in the sense that you can reach from every vertex to every other vertex. That's connected. We say it's connected. And if there is some other set here, if this is your graph, then let's say this is V1, V2, V3, V4, and V5. And this is V6, V7, V8. Then the connected sets here are V6, V8, and V7. This is connected. And V1, V2, V5, V3, V4, these are also connected, right? So this is called these are called connected sets. This is also connected. Now, if I remove this thing, this edge, it's still connected, right? If you look at just this thing, if you just focus on this thing, let's say you have this thing here. V1, V2, V3, V4, V5. Do you think it's connected? This graph is connected, right? Because from every vertex, you can reach every other vertex. So this is a connected graph. If I remove this edge, it's still connected, right? And if I remove this one, it's still connected. If I remove this one too, it's still connected. Now we have to be careful because if I remove one more thing from here, it's not connected anymore, right? This entire thing, this entire graph is not connected. So this is then a minimally connected graph, minimally connected graph, right? Which is called a tree. This is minimally connected, minimal connected graph. If I remove one minimally connected graph means if I remove one more edge from here, it won't be connected. That means this is connected, but if I remove one more edge from here, it won't be connected anymore. That's your minimally connected graph, which in simple terms is called a tree. Now let's discuss what a BFS tree is. Let's draw a BFS tree for this. The BFS tree has levels here, level 0, level 1, and level 2. And you start with the vertex that you were using, that you started with. So if you have to find the reachability and everything from V1, and that vertex is given to you in the questions and all. So if you start with V1, because we started our search from V1. Then on level 1, we just have V1. Then on level 2, on level 0, we just have V1. On level 1, we'll have the vertices that are directly connected to V2. V1 that are directly connected to that have a direct edge with V1. So V2 has a direct edge with V1. V4 has a direct edge with V1. That means on level 2, you should have V2 and V4. Then on level 2, you will have the ones that don't have a direct edge with V1, but they are connected via two edges from V1 to V2 and then from V2 to something else. Similarly, from V1 to V4 and then V4 to something else, right? So it's V1, V2, and then from V2, you can go to V6. So V6 is here on the
Ma'am,
second
could you
level.
please explain it again?
We start, if this is the performing breadth first search on this entire graph, and we start our search from V1, right? So to make a BFS tree, and these levels are not even important, you start with V1 and you see which ones are directly connected to V1. You write them here. So these are directly connected to V1. Or you don't even have to do that because, okay. So first you write V1, then you write the vertices that have a direct edge with, by direct edge, we mean these two. V2 has a direct edge with V1. V4 has a direct edge with V1. V6 does not have a direct edge with V1, but it has this path, right? From V1 to V2, and then from V2 to V6. That means V6 should be here, under V2, right? Then what else is under V2? Does V2 have an edge with something else other than V6? Do we see something else here? No other vertices, right? So V2 does not have a direct edge with anything else. So this is done. Then coming to V4, V4 has a direct edge with V5, and that's it. That means you have this thing here. And all of these, notice that all of these
And what
vertices are
about
mentioned there.
V4 to V2?
This is a tree. That's how you, and this is not just a tree, it's a BFS tree. So BFS tree is not any tree. But we discussed this thing. If this is a tree, then can you have an edge here? Tree is a minimally connected graph. Minimally connected graph means it has to be connected, but there should be no edge. Can I not remove this edge? If you have this graph, can I say that this graph is minimally connected?
No, ma'am.
I can remove this edge. I can remove this edge. There are two extra edges. That means that the earlier graph was not a minimally connected graph. That means it was not a tree. So if I have an edge here, do you think this is a tree? Forget about BFS for a while. This is not even a tree, right?
No, ma'am, I got your point.
Okay. And BFS tree, by the way, you don't even have to get into the details of tree and all. BFS tree is it's constructed this way. You write the first vertex with which you begin your search, and then you write the consequent vertices. These ones on level 1 are the direct ones. If there's a direct edge from V1 to V2, so you'll have this. Then from V2, you have a direct edge till V6. So this one and this one, that's it. And all these ones are here in this tree. So all the ones that you see in your queue or that are reachable from vertex B are also here. Vertex V1. Is the BFS tree clear?
Yes,
Now
ma'am.
let's say you have a BFS tree this. You have this BFS tree. You have V1, V2, V3, V4, V5, V6, V7, V8, and V9. Let's say you have this tree. Let's say this is a BFS tree for some graph. Right? We don't know what the graph is. And there could be more than one graph which can have same BFS tree. There could be graph 1 which has this tree as BFS tree when we start from V1. There could be another graph 2 which has the same tree. So there's no unique graph. So what are the questions like? The questions are like, can this graph have this BFS tree, or can this be a possible graph for this BFS tree? Or if this is your BFS tree, then can this be an original graph? You will be given a graph or what that graph is. Or can the questions are framed like this? Can you have an edge? V2, V3 in original graph. Original graph means you don't know what the original graph is, right? And we already discussed that from just this tree, you cannot identify the original graph. There could be more than one graph which will have the same BFS tree. But the question is it possible for you to have a graph which has this BFS tree? And then in that graph, can V2, V3 be an edge? That's the question. So can you have V2, V3 as an edge in your original graph? Let's say G was your graph, and then the BFS tree corresponding to that is this. So can there be any graph, not just G, can there be any graph whose BFS tree is this? And it has the edge B2, B3. Can B2, B3 be an edge there? So for
No,
you to
ma'am.
decide if B2, B3 is an edge. Why? Why can B2, B2, B3 can, the answer is yes. It can be an edge, and we'll see how that can be an edge.
Depends
Let's
on
say you have
directed or
this.
undirected graph.
Sorry, what?
I mean, depend on directed or undirected.
No, it really does not depend on directed and undirected. You can, the thing is, if you have this graph, let's say, let's not go very far. Let's say you have this. Okay, even if it were, let's say it's directed or undirected, we'll take both one by one. Let's say this is your graph, V1, V2, V3, V4. Everything is same as this tree. The only difference we're taking is we're taking an edge here. We're taking the graph to be this. So we're taking the graph to be this. The same as this tree, but we have an extra edge here. This would be an edge in the original graph, right? What will be the BFS tree for this then? Can this not be a BFS tree for this? If you start from your search from V1, then you'll go to V2, V3, V4, right? And then from V2, you'll go to this one, this one, this one. All I'm trying to say is if this is your graph, then the BFS tree is this. Is this clear to all? Let's try to make the BFS tree of this, although it's not required. If you start from V1, BFS tree is V1, let's say it's this. Or if it's undirected, then it's even easier because you can go from V1 to V2. So on level 0, you have V1 because you're starting your search from V1. On level 1, you have all the ones that are directly connected to V1. That is V2, V3, V4. Then on the other level, you have the ones that are directly connected to V2, which is V5, V6. So if this is your graph, this is the BFS tree, right? We can't have an edge here because then it won't be a tree. So the BFS tree for this thing is the same as this one. That means you can have a graph where there's an edge between V2 to V3. And the BFS tree corresponding to that graph will be this, right? That means you can have an edge from V2 to V3. And by original graph, I'm repeating this over and over again, that there is no unique original graph for a given BFS tree. Then second is, let's say you have taken V2, V3. This time let's take V2 to V, one second. Let's take V7 and V3. Can you have V7, V3 as an edge in the original graph?
Yes.
V7 and V3. You can have that edge, right? Because even if V1, V3 and V7 were an edge in the original graph, you wouldn't draw it here because V7 has been, if you draw this here, you only, in the BFS tree, you only write vertices one time. So if V7 has been covered under V2, you don't cover it again under V2. That's the rule for BFS tree. So even if there were an edge from V3 to V7 in the original graph, because V7 has been written under V2, you won't be writing it again under V3. Right? So this can be an edge. Then let's
And
come
could
to
there be
V1.
any situation where one vertex cannot have an edge with another vertex?
Yeah, we'll
Like
discuss
V1
that
and
now.
V2
If you skip
okay.
one level, then you cannot have an edge there. So there's no edge from V1 to V7. Why?
But
Because if
V3
V1
and V7 are not interrelated, no?
interrelated as in,
Like V1 is related to V2, V2 is related to V7, but V3 and V7 are totally disjoint in that term sense.
are you talking about the BFS tree?
No, no, you're written it down, na? Like V3 and V7 are vertex.
This
Yes.
is if you can have an edge in the original. It's not an edge here, obviously. BFS tree cannot have an edge as V3, V7. That's we're not talking about the BFS tree, we're talking about the original graph. Can your original graph have an edge V3, V7? That's the question, right? So the original graph can have V7, V3 as edge. Now let's come to V1 and V7. Let's do this. V1 is here, V7 is here. Can V1 and V7 have an edge in the original graph? So if, let's say V1 and V7 were an edge here. Let's say this is your original graph. And let's say this is an edge here. So if this is an edge, you should be writing V7 under V1. Because V1 and V7 is directly connected to V1. It has a direct edge with V1. So you should have written it here, right? And once you write a vertex, you don't write it again here. The first is it's not written under V1, it's written here under V2. That means V7 should not have a direct edge with V1. If it had a direct edge with V1, then you would write it here, not here. Is this okay? That
And
means
is this
V1
situation only for the first vertex?
in this particular case, it's only for the first vertex. But if you have further levels, let's say you have V9, V10 here, then it could be for V4 and V10 too, V2 and V10 too. Basically, when you skip a level or you skip more than one level. This is level 0. Now, if you jump to, this is level 1, level 2, level 3. If you jump to level 3, that's a problem. From level 1, if you jump to level 3, that's a problem. So if you skip one level, that's a problem. Is that okay?
Yes, ma'am.
Okay. Just give me 1 minute. So this was all about BFS and BFS approach and BFS tree. Is this entire thing clear to all of you? Can we move to the DFS approach now?
Yes.
Okay. The next one is your depth first approach. Depth first means first you'll go in depth. And one thing that I forgot to mention here is that when you make this queue here, this queue has a rule which is first in, first out. That means the first thing that gets in, if V1 got in first, that means if V1 got in before V2, then V1 should be out first of this queue. That means it will get ticked first. If V2 is before V4, it entered V4 before V2. Sorry, if V2 entered V4 before, if V2 entered the queue before V4, then it will leave the queue before V4. That's the rule here. So it's called first in, first out rule. And then we have DFS approach, the depth first approach, which means rather than exploring the entire breadth first, what you do in DFS is if this is the thing, you start your search from here, then you write V1. Let's say you have something like this. V4, V5, V6, and V7. Let's say if this is your tree, then what you do is if you start from V1, you go to V2, second is V2, then V3, then V4, then V5. So what you're doing is you're exploring the entire breadth first. You get done with this vertex and then you go in the depth. That's the rule, right? In breadth first search. In depth first search, the rule is if you start from V1 and then you go to V2, then you have to keep exploring in the depth rather than going in breadth. So the depth is after V2, you should have V6. Then after V6, you should have V7. Keep going in the depth. This one, then this one, then this one. If you have something else here, V8, then go here. Then when you're done here, because there's nothing else left here, or let's say if you have this too, because no other vertex is left, right? Let's do the example. If you have this as your example, and we use stack here, it's the same thing. It's called stack, which is, let's say you're starting your search from V1. This is again an approach to check reachability. If you're starting from V1, let's say, then the next that you go to is, you can go to V3, you can go to V4, your choice. Every vertex that's directly connected to it, you can go to that vertex next. So if you're going to, let's say I'm going to V2, then instead of going to V3 that we used to do in breadth first search, we'll go in the depth of V2. So you can go to V7 or you can go to V6, right? Let's say you have this thing.
So, ma'am, we are not writing V3, V4, V5 as well.
Yeah, we won't write that. Why we're not writing that? Because we're going to visit them later. We're not visiting them now. We're going from here to here in the depth. Then we're going in further depth here. Then in further depth here. And unless there is no depth to explore, we'll keep going in the depth. Is that okay? So we'll go to V2. If we have gone to V2, then we'll go to V6 or V7. That's your choice. So I'm going to V6. Then after V6, you can go to V8 or V7. Again, your choice. I'm going to V7. Then after going to V7, now you can't go to V8 because V7 does not have an edge from V7 to V8, right? This is V8. So what you do is, from V7, can you go to any other vertex? There's no other vertex that you can go to. That has not been written so far, right? Yes.
Ma'am, if we go V6 to V8, then what will be the changes?
Okay, let's say you go from V6 to V8. Now you are at V8. Then you can go to V7, right? You'll continue in the depth, V2 to V6, then V6 to V7, then next to V8 and then to V7. So the next you'll go to V7. Then after V7, there's nothing left to explore, right?
Yes.
After V7, you don't have anything. Or let's say if you had this thing here. Let's take this edge to be this one. Even if you had this thing, that doesn't mean you will go from V7 to V2 because V2 is already done here. So you don't write it again. That means from V7, there's no other vertex left to visit, which has not been visited so far. Then you will trace back. You will come from V7 to V8, right? And then check if there is any other vertex that is directly connected to V8, which has not been visited so far. Let's say if you had V9 here, then I'll go from V7 to V8, trace back to V8, and then check V8 if it's done or not. That means V7 got done, now it's out of this stack, right? And this is also called for first in, last out. That means, or you can say last in, first out. That's also valid. That means the one that enters the last, V7 has entered the last, but it will leave the first. It got done exploring the first, right? We are done exploring V7. There's no other vertex that is left from V7. So V7 is out of the stack first, although it entered the last. Then we trace back to V8 and we check if there is any other vertex that you can visit from V8, which there is, right? We have V9. So we write
And how do
V9
we
here.
trace back to V8 even though there isn't even though the arrow sign isn't in that
Trace
direction?
back as in you have to go back here. That's why we say we're not using this tree to trace back. when I say trace back, I mean you have in depth. If you remember in breadth first, what we used to do was, if this vertex entered first, then first I tick this out, then I move to the next one, right? That means first I explore this one, and when we're done exploring this one, this is out of the queue, then we do this one. Then we do this one. But that's not the case for depth first. In depth first you get done exploring with the last one. So if you're done exploring with this one, you trace back to this one here. So it's easier to look in the in the graph itself, that you can go from here, you will go back to here. You don't need an edge for that. V8 has been visited. Why would you need an edge here? You would need an edge here if you need to visit V8, which already has been visited. It's in the stack, right? You don't need it. So we trace back to V8, and then from V8 you have V9. And from V9 there is nothing else. So you can trace back from V9 to V8, and V9 is done. So V7 was done, then V9 is done. Notice that the last one gets out first. V9 gets out first after V7. Then V9. Then you trace back to V8, and there is nothing left to explore from V8, right? Nothing else left to visit from V8. That means V8 is also done. No other vertex that you can visit from V8. You can visit V9, it's already done. Visit V7, it's already in the stack. That means V8 is done. Then you trace back to V6, where you came from, right? Or the last one. You don't even have to remember this thing. Just look at this one. The last one in the stack so far. So the last one is V6 in the stack. Then from V6, check which ones are there. V7 is there, V8 is there. They're already in the stack, V7, V8. That means V6 is also done. The order is important here. V7 got done first, then V9 got done, then V8, then V6. Then V6 is done, then you trace back to this one, V2. Forget about tracing back from here. You can just check directly from here which one is the last one. So V2 is the last one in this one, which is not done. So from V2, there is no direct edge. Or even if there is, it is already covered here. V6 is already covered. So V2 is also done. Then from V2, you go back to V1. Now V1 is not done. You can't say V1 is done because you have V3, V4, V5 that have not been mentioned, but they have an edge with V1, right? So you have come here. Then from V1, you can go to V3. So the next one is V3, this one. Now this is the last in the stack. So you check this one. There's nothing left to visit from V3. That means it's done. So it gets done first before V1. Then you go back to V1. Then from V1, there's V4. Same happens with V4. Nothing left to visit. So V4 is also done. Then you trace back to V1. V5, nothing left to visit from V5. V5 is also done. And then finally you trace back to V1. And there is nothing left. V2, V3, V4, everything is covered. That has a direct edge with V1. That means V1 is also done. So that's your depth first search. Is this clear to all?
Yes, ma'am.
Okay. So then we have a definition of components. Components in a graph are basically your maximally connected sets. Maximally connected set of vertices means, let's say you have this graph. And then you have this. V1, V2, V3, V4, V5, V6, V7, and V8. So because this entire thing is connected and it's maximal, right? Now you cannot add, you have V1, V2, V3, V4 connected, and you can't add V5 to that set because V5 is not connected. So this is one maximally connected set. it's one component. This is called component. First, this is one component, and the other component is this. Second component. And if you had something like V9 alone, then this will be the third component. So the definition, it's called maximally connected collection of vertices. That's component. And if you have, let's say you have BFS, if you have to identify the components, can we use BFS and DFS for that too? Because it will perform BFS and DFS approach. Then you can obviously see which ones are the component, like from this one. The component here is this entire thing. Now, what happens if we had something like V10, V11, and V12 here? Let's say we had this thing too. Then this will get covered. So everything that gets visited from V1 or any other from V1 would be one component, right? And then this one won't be a component. Component in the sense it won't be a part of this component. It's a different component. Or not actually this one. Your BFS helps you identify this better. So your BFS approach helps you identify, actually both of these help you identify components too. They help you identify components, but you're not asked to find the components and all as such. Is this okay?
Yes, ma'am.
Okay.
The recording will be available.
Yeah, it's available on YouTube.
Okay, ma'am.
And then we have cyclic graphs and acyclic graphs and all of that. So cyclic graph is basically if you see a cycle there, if your graph is like this, basically if it is closed. In in an undirected graph, it looks like this. A cycle looks like this, or it looks like this. If it's closed, then that means this graph has a cycle. If this is your graph, let's say, if this is a graph that you have, then this is a cyclic graph because it has a cycle. What's your cycle here? This is one cycle. In fact, you have two cycles. One cycle and two cycles. Both of these are cycles. And in a directed graph, cycle looks like this. This is a cycle. You can go from here to here to here to here. It's closed. Right? And this is
Ma'am,
not a
if any
cycle.
of
Yeah. Was someone saying something?
no, ma'am, I understood with the second example.
Okay. So, and a cyclic graph is one that has a cycle, and acyclic is no cycles at all in the graph. And
So 3 ages means not cyclic.
which one? This one is not cyclic because you go from, for a cycle it should be like this. It should follow a direction like this. Now this is a cycle. The upper one is not a cycle. This one's not a cycle. This is a cycle. Because it's following a particular order, right? From here to here, then from here to here, then from here to here. This is not following any order. This one, and then it's opposing the direction. And then we have, let's do DFS tree. The same as BFS one, but it's obviously made using different technique. So DFS tree is basically for you to make a DFS tree. Let's say what was a graph the last time? We'll draw the DFS tree there. Let's make the DFS tree here. So we'll start with V1. Then we have V2. Then V6. Then V7. And by the way, in BFS tree 2, you can change the order of these. You can write V3 here, V2 here, V4. You can change the order of these. That's not a problem. And in a DFS tree, you start with V1, V2, V6, V7. We're going by what we did here. We went from V1 to V2, then V2 to V6. Then instead of going to V7, we went to V8. That's why we're making it this way. V7 to V8. Sorry, we did V8 first, right? Yeah. We did V8 after V6, then V7. That's what we followed, right? From V2 to V6, then V8, then V7, then trace back to V8. Then V9 here. Then trace back to V8. Then trace back to V6. Then V2. And then V1, right? And then this V3, V4, V5, right? So this will be your DFS tree. So your DFS tree is drawn this way. You have to do the same things, but in the depth order. Is this fine? Or shall we do one more example of this? We need one more example on DFS tree, or is this one clear? All you have to do is you have to follow the same thing that you did in stack. You started from V1, then you went into the depth V2, then further into the depth V6, then V8 you visited, then V7. So V1, V2, V6, V8, V7. Then you went back to V8, V6, went back. By went back, I don't mean that you go from here to here. I just mean that in the stack, you chose V8 next. Then from V8, you went to V9, then back to V8, back to V6, because V6, V8, all of these are done, are explored. Then from V6, because it's explored, then to V2, then to V1, and then V3, V4, V6, V5 in this manner. Is this fine? And you can have one more BFS tree. Let's do one more. You can have V1, V2. This is also a possible this is also a DFS tree for this. You go to V2, or you can go to V3. Then you go to V2. Then from V2, you go to V6, and then to V7, and then to V2 to V6, then to V7. Then after V7, you won't have anything, right? So you'll get back to V6. Then from V6, you'll go to V8. Then from V8, you'll go to V9. Nothing left from V9. So back to V8, back to V6, back to V2, and then back to V1. And then V4, V5. This is also a DFS tree. This is one DFS tree. This is another DFS tree. Both of these are different. This ordering is also different. This branch is also different here.
Ma'am, it means that one graph can have multiple
Yeah, it can
DFS
have
tree.
multiple DFS trees, right? Okay. So then we're left with the finding the components. Let's see how we find the components, right? Let's say you start from, let's say you have this thing. You have, let's say you have vertex 1 here, then vertex 2, then vertex 3, vertex 4, vertex 5. And then you have vertex 6 and 7 here. Let's say you have this thing. So if you have this thing, and let's say we're starting with V2 this time. Let's start with some other vertex instead of V1. You can start from here too. That's also fine. Because we're trying to identify components. Let's start with V1. Then you go to, and let's directly make a tree instead of doing that stack and everything, because that's not needed. So you started from, let's say you start from V2. Then from V2, you can go to V1. Then from V1, you can go to V3. Let's make the directions too. Let's do this. So you started from V2. You can go to V1. Then next you can go to V3. Then from V3 you can go to V, but V2 is already done. So then to V5. Then from V5, can't go to V4 because this is pointing in the other direction. Then you will trace back to V3, right? You're done exploring V5. The end has come. After V5, you can't go anywhere. By anywhere, I mean you can't go to any other vertex which has not been visited so far. A new vertex other than these. So you trace back to V3 here. Then from V3, you can't go to any other new vertex except V2, except for what are already visited. Then you go back to V1. Then from V1, you can't visit anything new. So go back to V2. Then from V2, you can visit V4, right? So write V4 here. So this one will be, this will be the DFS tree if you start from the vertex, from the second vertex. But we were trying to find components, right? So this is one component. This entire is one component. And we keep tracks of when we visit and when we leave. So when we started from V2, we keep pre-post number here. This is called pre number. This one. The one you write on the left is called pre number. And here, what you write is called a post number. So why we use these numbers is to keep a track of when you visited and when you were done exploring that vertex. So let's say you started. So 0 means you started this first. Then you went to this. Then you visited this. So the next number is 1. Then next you visited this, second. Then next you visited this, third. And then you got done exploring this, right? That's what the order was of visiting the vertices and then getting done with exploring the vertices. So this gets explored first. So fourth number here. You put a post number here when you're done exploring that vertex. Pre number when you're visiting that vertex. So a number 4 here. Then you go back here because there was no other vertex to visit from V5. So you go back to V3 and then you're also done exploring V3. So you put a post number here. Next one, 5. Then you go back to V1 and you're also done exploring V1. So you put a post number here too, which is 6. Then you go back to V2 and you're also done exploring V2. So you put a post number 7 here. No, V2 is not done, right? V4 has not been visited. We're not done exploring V2, done exploring V1 with post number 6. Then from V1, you come here to V2. And we're not done exploring V2. That's why we don't put a post number here. Then from V2, we go to V4. So because we have visited V4, That's why we put a pre-number here, 7. After 6, 7 pre-number. And because there's no other vertex left to visit from V4, so we're done exploring V4, put a post number here, 8, go back to V2. We're done exploring V2 too, because there's no other vertex left from V2. Put a post number here, 9. So this component is done. Then we come to the other component, this component. And the convention is that this is just a convention. It's not a rule that you start with the minimum one, the minimum numbered vertex, V6. And then from here, so you've ended here with 9, right? So you put a pre-number 10 here. Although these are not connected, but we start from here for the second component. So this is component 1. And the second component is, and the numbering does not matter. The component numbering does not matter. So from V6, the pre-number is 10. You go to V7. You can also go, you can't go to V8, right? So V7, from V7, you can go to V9 or V8. So I'm going to V9, then to V8. And then we're done, right? So from V6, we went to V7, and we're not done exploring V6 because it will get done the last. Remember, I said V6, then V7, then V8, V9, then V8. If this is your stack, this gets out first. That's why this will get a post number first. So 10, 11, 12, and then this one is 13, and this will get the post number first. This will get out first. So 14, then this will get out next. So 15, then this one, 16, and then this one will go out last, 17. Is this okay? Are the pre-post numbers clear to everyone? This will be your other component. Then we have something called tree edges and non-tree edges. So tree edges, are basically the edges in this tree. This is a tree, right? So the edges in this tree, the edges in your graph that are also present in this tree that you've made. So this is and this is only, and everything that we're discussing here is only for DFS1. This counter and pre-number, post number, and tree edges, non-tree edges that we're studying, this is only for DFS approach and all, not for the BFS1.
Ma'am, does the BFS
So,
approach to have some sort of numbering like this?
no, it does not have any numbering there. No numbering there, only in BFS1. So your tree edges are basically the edges in your graph that are also present in your tree, like V4, V2, and V4. So there's an edge in your graph, V2, V4 is an edge, and it's also present in your graph. That's called a tree edge. And non-tree edges are basically the ones that are not in your tree. So if you see here, which one? V4 and V5 is an edge here in your graph, but it's not there in your DFS tree, right? So V4, V5 is example of a non-edge, a non-tree edge. And there are 3 types of non-tree edges. So one is a forward edge. Then you have back edge. And then you have cross edge. So your post pre-numbers and post number help with this. Let's say you have an edge UV, which was there in the graph, but it's not in the tree, right? That means it's a non-tree edge. So UV is a non-tree edge. And let's say the post number and pre-number for U were, pre-number is let's say 4 and post number is let's say 10. And the pre-number and post number for V is let's say 5 and 6. So that means U, what do you think would be the direction? This one or this one? because you started, this has a lower pre number. That means this got visited first, right? And this got done exploring after this one. This got done exploring first. We explored this one first because this has a lower pre number, post number. So what it is you visited U, then you visited V later, then you got done exploring with V, and then you got done exploring with U, right? As per the pre numbers and post numbers. That means your edge should be in this direction, right? There might not be a direct edge in the tree. It could be that you have this and it's somewhere here. It got visited via some other edge. So your tree might be something like this. B and something W here. Or maybe W1. So you'll have a number 5 here. Or if you have 5 here, that means this was B edge. So B and then 6. And then let's say it has something else too. W1, which has number 7. Then some other edge, W2 with number 8, 9, 10, and let's say this is 11. So that what I am trying to do here is that means this is, if this is a non-tree edge, then it's a forward edge. You don't even have to remember all of this. This is not important at all. My entire point is that you visited this first and explored this later. You got visited first, explored later. Then we got visited, then we got explored. In this order, things have happened. Then you got explored. That means it's a forward edge. It's pointed in this direction from U to V. That means it's a forward edge, right? And let's say now the opposite happens. The definition is as this. Let's say the pre-post numbers, if you have an edge UV, for forward edge. So UV is called a forward edge if pre-number and post number. When you take pre-number and post number together, they form an interval, right? Like 4 and 11, this is an interval. 5 and 6, this is an interval. Because this 5-6 interval is contained in 4-11 interval, that's why it's a forward edge. That's the definition of forward edge. Pre-number of V, the one that's written later. If UV is an edge, U to V, and if pre-number post number of V interval is contained in pre-number post number of U. Then it's a forward edge. UV is a forward edge, like in this example. Pre-number post number interval of V is contained in pre-number post number of U interval. That's why this one is a forward edge. Now let's change things here. Your U was 4 to 11 and V was from 5 to 6. Let's say if this was an edge, then this would be called a back edge. So for back edge, what you need is, it's the opposite of forward edge. Back edge is, we say UV is a back edge, U to V, if pre-number post number, pre-number of U and post number of U. We're changing this. Here we had V and U. Now we're changing this pre-number, post number of U is contained in, that means this thing now is contained in this one. Pre-number, post number of V. If this happens instead, that means it's a back edge. That means if you have an edge from, let's say you have an edge from V to U, we have reversed the directions of the previous one, of this one. We have reversed the direction of this edge. So now it's from V to U. So now what you have instead is, you have the edge is VU, right? This edge is VU. And the pre-post numbers of U, the one written later, U is written later. It's from V to U. So this the pre-post number of U, that interval is contained in pre-post number of V, right? That means it's a back edge. And then we have the last one, which is a cross edge, which is this. Let's say you have pre-post number UV. Let's take UV. So UV is a cross edge if pre-post number, pre-number, post number of U, this interval, and pre-number, post number of V, this interval. If the intersection of these two intervals is empty, then we say that it's a cross edge. Like let's say you have U and the pre-post numbers are 5 and 10, and V, it's 11 and 13. Then this interval 5 to 10 and 11 to 13, the intersection is empty, right? That means UV is a cross edge. So if there is an edge from U to V in the original graph, which is not there in the tree, then it's a cross edge, right? Shall we do one example, or is this? Let's do this example. Let's say you have this, right? Now, if you'll make the tree of this, it will be V1, starting from V1, 0 counter, then at V2, you'll have 1 pre-number, then at V3, you'll have 2 pre-number, then you will end the pre-number, the post number here will be 3, then here, one, 2, 3, 4, 5, right? Now, we have only made these edges, right? These ones are 3 edges. V1 to V2, V2 to V3. 3 edges, because they're also in the tree. V1 to V3, however, is not in this tree. That means it's a non-tree edge. And what kind of non-tree edge is it? V1, if you will make it dotted here, you will see. What's the pre-post number of V1? It's 0, 5, right? This interval. And the pre-post number of V3 is 2, 3. And 2, 3 interval, this one, the pre-post number of the one later, written later, V3. The second entry. The pre-post number of this is contained in pre-post number of V1. This is for V1, this is for V2. And because 2, 3 is contained in this interval, that means V1 to V2, this is a
And that should be V3.
forward edge, right? Yeah, V3. It's a forward edge. Now, if instead the original thing was, this is your original graph, right? Now, instead of this, if you add this, V2, V3, then you will have V1 visited, then V2, then V3. You will have 0 here, 1 here, 2 here, 3, 4, and 5. Same DFS tree. 1 second. V1 to V2. Yeah, same DFS tree. But now your edge is, it's not V1, V3. V1, V3 is not even an edge in your graph. So it can't be a non-tree edge. All your non-tree edges and tree edges are from your graph. The only difference is tree edges are present in the tree, the DFS tree. Non-tree edges are not present in the DFS tree. That's it. But both of them are in your original graph. This is your original graph. So they should be in the original graph. So V1, V3 is not even an edge this time, right? So we can't discuss whether it's a non-tree edge, tree edge, because it's not even an edge. So we'll have to take V3, V1. So V1, V2, this is a tree edge. V2, V3 is a tree edge. V3, V1 is a non-tree edge. And what kind of non-tree edge is it? So this time, the pre-post number of V1. Pre-post number of V1 is 0 to 5. And pre-post number of V3 is 2 to 3. So for a forward edge, you want the pre-post number of this to be contained in pre-post number of this, right? And for a back edge, pre-post number of this should be contained in pre-post number of this. This is for V1, this is for V3. So this should be a back edge. This time it's a back edge. And for cross edge, you'll have something from a different, an entirely different point here. This. Now, if you'll have this thing, you'll have the tree as V1, V2. This is your DFS tree, right? This time your DFS tree would be this, starting with 0, 1, 2, then 3 here, 4 here, then 5 here, 6 here, and then 7 here. So let's say this is an edge here. If this is also an edge, then V3, V4 is an edge in your original graph. This is your graph. This is the DFS tree. Now pre-post number of V3, this interval is for V3, it's 3, 4. For V4, it's 5, 6. And the intersection of both these sets, both these intervals, because this and this have nothing to do with each other. This is empty. That means V3, V4 is a cross edge. And with this, we're done with all type of edges. We're only left with one more topic, which is DAG and directed acyclic graphs and topological sorting. So we'll discuss this in the Tuesday class. We have a class on Tuesday, which is supposed to be a doubt class. So these are very small topics. We can discuss those there. Is that okay? Does anyone else want to ask anything else?
Yes, ma'am. We'll discuss the same thing again. The last week you discussed this topic, yes.
I couldn't hear you. Can you repeat?
Ma'am, this last topic.
Yeah, this one
No. This.
or this one?
Yeah, please,
Okay.
we'll discuss this one.
Should I repeat it now? Okay.
No, that day will be fine. No problem. I will read again and.
Okay. If you have any doubts there, because it is a doubt class, you can ask for doubts there. In theory, in questions, assignments, you can ask the doubts there.
Okay, ma'am.
Okay. So if there is nothing else, can we stop this session
Ma'am,
here? Yes.
I have a question.
Yeah.
We saw that one graph can have multiple DFS trees.
Yeah.
Is this the same for BFS trees as well?
Yeah. Then we discussed if you write, so we were discussing this thing, right? If on level 1, let's say you've written V3, V4, V5 in this order, the order does not matter. So you can have V4, V3, V5. Obviously, the levels won't change. If you have on level 1, if you have vertex 3, vertex 4, vertex 5, then in any other BFS tree, those same vertices will be on level 1. So the vertices don't change on the levels, but their orders in which you write them, right? That does not matter. So you can change that. although that's considered the same thing. So they're not are you getting my point? They're not considered two
Yes.
different BFS trees. They're considered the same BFS tree. So because you
Okay.
cannot change the number of vertices, if V1 was on first level, it has to be on first level in every BFS tree. So in that sense, your BFS tree is unique. Yes.
Okay, ma'am, got it.
Okay. Does anyone else has anything else? Or we can take up the doubts in the next class. If there's any doubt, you can ask that in the next class. Is that okay?
Okay, ma'am.
Okay.
When next class happen, ma'am?
It's on Tuesday.
Okay, ma'am. Thank you.
Okay. Thank you.